different ways in machine.
Sorry.
No problem. Do you want me to start again just so it's on the recording for future?
Yeah, sure.
Okay, cool. Hey everyone, I'm Priya Donti. I'm a co-founder and chair of Climate Change AI and a PhD candidate at Carnegie Mellon University. And today I want to tell you a bit about the different ways in which machine learning can be used to help address climate change. Throughout the presentation, feel free to drop questions in the chat. And I'll try to get them to them as we go. And of course, hopefully there'll be some time at the end for Q&A as well. All right, so diving in, climate change is, of course, if you're here, you probably believe, right, one of the most pressing issues that society is facing today. And we're already feeling its effects, from storms to droughts to fires and flooding and so forth. These impacts are being felt globally. There's no place in the world that will not be affected by climate change. And unfortunately, the impacts are being disproportionately felt by the world's most disadvantaged populations. And this creates a real need and imperative to act on addressing climate change quickly. In particular, according to the UN Intergovernmental Panel on Climate Change, we will need to hit net zero greenhouse gas emissions by 2050. That means putting in no more greenhouse gas emissions to the atmosphere than we're taking out. And in order to achieve that goal, a lot of the key technological and policy and social decisions will need to be made within the next decade or so. But we're unfortunately still in a situation where greenhouse gas emissions are increasing year after year, again, underscoring the need for really rapid action here. And when I talk about climate action, I'm talking about two major categories of actions. One of these is climate change mitigation. The idea that if we reduce the amount of greenhouse gas emissions that we put into the atmosphere, then this reduces the amount of climate change that we actually experience. Another axis of action is climate change adaptation, which means given that we already have put greenhouse gas emissions into the atmosphere and we are going to experience some climate change effects as a result, how can we build resilience to these consequences of climate change? And I bring these two avenues of action up because people often ask me, you mentioned this net zero by 2050, we need to make major decisions in the next decade. Is it too late to act on climate change? And the answer to that is no. Every single unit of greenhouse gas emissions we avoid putting into the atmosphere today creates a better scenario going into the future. And in addition, we will also want to continue to take strong actions to adapt to the effects of climate change that we'll face. So climate change is not an on-off switch. Everything that we can do today in order to mitigate its effects will create a better situation going forward. And one thing about climate change is that there's no one silver bullet solution. We have to kind of create change across the entirety of society in order to address it. So what this plot is showing, it's a plot from the World Resources Institute, which is basically showing the sources of greenhouse gas emissions broken down by sector in the first column. So you'll see, for example, electricity and heat make up about 30% of greenhouse gas emissions, but you also have agriculture making about 12, transportation about 16, and so forth. So there's not one sector that is sort of making up all of the greenhouse gas emissions. It's distributed among many different sectors. And on the one hand, this can look a little bit daunting, right? It would be great if there were just one simple action we could take to avert the entirety of climate change. Unfortunately, that's not the case. But flipping that on its head, it's an opportunity for those of us who want to address climate change. There are many different ways to plug in and actually make an impact. In particular, given the sort of, the focus of this particular event, a lot of us are coming from a data science background, and we might be asking the question, if we want to use our data science and machine learning skills in order to address climate change, how do we actually do that? So about 2 years ago, a group of co-authors and I wrote a paper called Tackling Climate Change with Machine Learning that tries to address exactly this question. It tries to identify the different places in which AI and machine learning could potentially play a role in helping to address climate change. And in the paper, we go through basically, some of the different sectors that you saw that are kind of emitters of greenhouse gas emissions. So electricity, buildings, transportation, industry, and so forth, to think about how can AI and machine learning help us to reduce greenhouse gas emissions in those sectors. And we also talk about ways in which AI and machine learning can help with climate prediction, with societal adaptation, with policy, help us actually adapt also to the effects of climate change that we're going to face. So for those of you who are interested in this, I would definitely encourage you to check out the paper, or also we have some interactive summaries online that I actually have the link on the previous slide here. And it gives you, several dozens, like hundreds of applications where you can actually make an impact here. But today I want to go through 7 example applications to give a sense of the kind of, breadth of ways in which AI and machine learning can plug in. And hopefully some of these will also inspire you in terms of particular directions you might be interested in taking in your own work. Yes, and I'll share a link to the paper with you afterwards, but if you can also Google tackling climate change with machine learning. But yes, I'll share a link. All right, so diving into, thank you, Luis Mario, for sharing the link. So so the first application I want to dive into is forecasting supply and demand on electric power systems. So the kind of transportation and production of electricity make up about 1/4 of greenhouse gas emissions. And on electric power grids, we need to always maintain this constant balance between electricity supply and demand. So the amount of electricity that we put into the electric power system has to exactly equal the amount of electricity we're consuming from it at every single moment. And you can imagine that this can be tricky because both the amount of power that we consume changes from moment to moment, sometimes in sort of unpredictable ways. And also, as we start to incorporate renewable energy, things like solar power and wind power, whose output varies based on the weather, the amount of electricity supply we have also changes. So how do you maintain a balance between electricity supply and demand when both of these quantities are a bit uncertain? So one way machine learning has come into play is to provide short and medium-term forecasts of electricity demand and electricity supply. So there's been a lot of work that has used some combination of historical data, the outputs of physical models like weather models, and even image and video data, things like a camera is sitting next to a solar panel pointed at the sky that can tell you something about how the clouds are moving above that solar panel. Machine learning has been used to take in these heterogeneous sources of data and provide short and medium-term forecasts of electricity supply and demand in a way that actually helps power system operators to balance the grid, even when there are large shares of renewables on the grid. With all of these applications I'm going to talk about today, there's always this question of who is the stakeholder, who is the user for this work in order for it to actually have an impact. So in this case, the sort of stakeholders who can make use of electricity supply and demand forecasts are power system operators, also power producers. So if you own a wind turbine, for example, you often need to report to the power system operator, this is how much I think this wind turbine is going to produce. So having better forecasts can actually help you better participate in the electricity market. And there also is a notion of demand aggregators on the electric power system that help to shift when power is used on the power system from time to time. And electricity demand aggregators can also make use of this information in order to help flexibly manage electricity demand on the system based on how much electricity supply is actually available. So while there's already a lot of work using AI and machine learning for forecasting, there also is some novel research trying to further improve some of the methods that are used here. And these includes methods that try to, incorporate more knowledge of the physics of the electric power grid in order to improve forecasts of electricity demand or electricity supply. And also methods that try to, put error bars on these forecasts, characterize the uncertainty in these forecasts so we can take that confidence information into account when actually managing the electric power system, and also work that tries to make forecasts more interpretable so that if something goes wrong, we can understand what about the forecast actually made that happen. So forecasting is just one example of the ways, one example way in which AI and machine learning can plug into electric power grids. And this schematic on the slide is showing sort of, this very large figure of different ways in which AI and machine learning can plug into the sector. So in addition to forecasting, there are lots of machine learning algorithms that try to optimize the electric power grid more quickly and dynamically based on real-time data that you're seeing on the system. And also, applications that try to actually, charge batteries or discharge batteries or otherwise control devices on the power grid in order to actually integrate renewable energy. And this is actually where my research, my PhD research lies. My research looks at ways to actually create machine learning models that can, incorporate some knowledge about the physics, hard constraints that exist on the electric power system in order to make sure to satisfy them. On the electric power grid, if you implement a method and it sort of breaks the physics of the power grid, that can lead to multi-day blackouts and loss of lives. So you really want to make sure that you're incorporating some of this physics and hard constraints into the way that you're designing machine learning methods on power grids. And so my work looks at doing something, at addressing this problem using a specific tool called implicit layers in neural networks. So I'm not going to go into this in detail, but the idea being that, on electric power systems, there are both things that you can do today using existing technologies like forecasting. And there also is a lot of opportunity for innovation and research to try to tackle some of the specific domain-specific challenges that come up when you're working in this area. So another sector in which AI and machine learning has been used is in the building sector. In particular, the idea is that we need to increase the energy efficiency of both existing and new buildings in order to reduce the amount of emissions that they're producing. Buildings are about, depending on how you account for it, residential and commercial buildings can be, something like 10 to 20% of global greenhouse gas emissions. So this is, again, a share that we really want to reduce. Machine learning has been used in a couple of ways here. One of them is to sort of help city planners or policymakers figure out where it makes the most sense to retrofit buildings, to actually make them more energy efficient by, for example, installing insulation in the buildings. And there's been some work that tries to combine weather data and information about building characteristics in order to predict, how much energy a building is using, and also how much energy could be actually reduced in that building's usage in order to then predict energy retrofits. And this is actually the topic of this year's Datathon, the WIDS Datathon this year. So those of you who are interested in learning more about that, I would definitely encourage you to check out the Datathon and potentially get your hands dirty with some of the data there. Another application that exists here is the smart control of equipment in buildings. So heating and cooling systems in buildings make up about half of the emissions associated with buildings. So there's been a lot of work that tries to actually dynamically control the heating and cooling systems in buildings based on things like the external weather, the thermodynamic characteristics of the building, and also things like the occupancy patterns in the building, who is actually, how many people are coming in and out of the building at a given time. There have also been initiatives that have tried to use machine learning to optimize lighting in buildings, and even beyond just residential and commercial buildings in the sense of buildings that you and I might occupy on a day-to-day basis. We also want to talk about industrial buildings like manufacturing plants. And there's also been uses of AI and machine learning to actually optimize industrial equipment in a way that reduces their energy usage. The kinds of stakeholders that one might want to work with if you're working on this topic include, building managers who might be managing a commercial building, city planners who might be looking at an entire city and asking this question of how do I structure, financial incentives and rebates in order to target building energy retrofits, and also equipment manufacturers. Definitely, there are lots of manufacturers that are, putting out heating and cooling equipment or lighting equipment, and sort of baking in some of these smart control methods into that equipment can be one route to impact here. So moving on to the transportation sector, there are lots of different ways in which we can sort of use AI and machine learning in the transportation sector. But one need I want to point out is the need to create next generation batteries or alternative fuels in order to move us away from fossil fueled transportation towards clean transportation. The challenge as we develop next generation batteries and alternative fuels. So in order to make batteries, a very viable alternative for things like electric vehicles, or even helping us more efficiently manage renewable energy on the power grid, we often need to bring down their costs, and we often need to improve their energy density, which means sort of for every kind of, amount of space that they're taking up, how much energy are they actually able to store? And this can be really important if you want to start to, do things like put a battery in a vehicle that is very, very heavy, because it's, for example, transporting freight. We need batteries to be really energy dense. And another way that people have tried to address this is say, can we actually create liquid fuels, which are really, really energy dense, but that are coming from, cleaner sources rather than from fossil fuels. In all of these cases, how the discoveries of these, next generation batteries or alternative fuels work is that we tend to have some experiments where we've tried to synthesize these kinds of things in the past. And then we look at those experiments and we try to say, okay, I tried to synthesize this particular battery in the past. It didn't work for this reason. Maybe let me try out a different battery design next in order to see if that works. And this really goes by trial and error. And each cycle of this can take months to years, where you design a particular battery, you synthesize it, and it takes you months to years to actually test it, which means that the overall cycle of developing batteries can be really, really slow. So what machine learning has been used to do is actually try to say, let's look at this data on past experiments and learn some patterns in that in order to recommend which experiments it might be most fruitful to try next. And as a result, this can reduce the number of tries that you need to take in order to synthesize that next battery. And as a result, kind of reduce the total time it takes in order to synthesize that battery. And there are already companies like Aionics based in the Silicon Valley that are actually doing this kind of thing in order to provide input to electric vehicle manufacturers or battery manufacturers in order to help them reduce the cost or improve the quality of the batteries that they create. Which brings me to some stakeholders here that you might want to work with if you're interested in this area are research and development labs who might be creating next generation batteries, electric vehicle manufacturers, and also participants in the electric power system. Batteries are also, again, you don't just put them in electric vehicles, for example, you also often put them on the electric power grid so that you can charge them with solar power when it's available and then use that solar power, stored solar power later on when it's needed. So batteries sort of play a big role in both transportation and electric power systems. All right, so moving right along to the sector of heavy industry. So as many of us have maybe even increasingly experienced during COVID, we've definitely started to get a lot of packages and shipments to our houses, and these are sort of moved to us by the global logistics and supply chains, basically, that take goods from where they're manufactured and produced all the way to where they're consumed. And there's a real need to make these global supply chains more efficient, to decrease the emissions that are associated with actually sourcing and delivering these kinds of goods. So machine learning has been used in a couple of different ways here. One of these is to try to cluster suppliers in order to reduce the number of shipments that are made, which is to say, if you can identify different suppliers that are transporting things from similar places to similar places at similar times, you can potentially, bundle the shipments that they're sending in order to reduce the amount of sort of freight miles that you need to travel in order to actually transport those goods. There's also in the freight and logistics sector, there are these things called freight auctions that actually determine, what trucks are transporting what goods. And there are also all these complex systems that actually determine how freight is routed. So machine learning has also been used to actually more dynamically route freight and improve freight auctions in order to also be resilient to things like if one train gets delayed, how do you dynamically change the routing of your goods in order to improve the efficiency by which they're routed. And then there's also been a use of machine learning to predict the amount of demand that there might be for a particular good more precisely in order to reduce the overproduction of that particular good. So this can also be one way to sort of reduce waste in this sector. The stakeholders that come into play here are logistics companies. So these are the companies that, manage how actually, freight and transportation actually move and are scheduled, and also the rail and freight companies themselves. With all of these kinds of applications, though, it's really important to beware of something called rebound effects. A rebound effect occurs when you make something more efficient, and as a result, it gets used more. So for example, if you make transporting goods more efficient, and as a result, they cost less to transport, it might be the case that you want to now transport more goods and you potentially eat into some of the emission savings that you got in the first place. So when you're implementing machine learning methods in these kinds of environments, it's really important to be cognizant of sort of these kinds of rebound effects and other effects that can occur because of what you implemented, and take that into account both in the design of your method and when thinking about how that method is actually going to be used. Okay, so the sectors I've talked about so far, electricity, buildings, transportation, and industry, are sort of under the broad umbrella of energy-based emissions. The emissions in those sectors are coming from the fact that you are using electricity or energy in some form and sort of turning that into some kind of action, and that creates emissions. Now, moving on, there's a sort of separate set source of emissions, which is emissions from land use. So from, for example, the way we farm or our forests, there are sort of emissions associated with this kind of land use. And the challenge is actually, we tend to have a pretty good sense on a global scale of, what our energy-based emissions are. So we tend to have a pretty good estimate of the amount of emissions that we have coming from electricity, buildings, transportation, industry, with some exceptions, but again, just generally a pretty good sense of this. But when it comes to land use emissions, things like how much emissions are coming from our soil or from our forests, we actually tend to be more uncertain about this. So there's a real need to get a better estimate of the amount of greenhouse gas emissions that we have and how our land is actually being used in order to help us better simulate it, in order to help us better account for the greenhouse gas emissions that come from that, and in order to help us frame better policy in these kinds of sectors. So one way machine learning has been used here is through remote sensing. The idea being that if you have access to large-scale satellite imagery or aerial imagery or drone imagery, then you can actually apply machine learning to that at scale in order to detect objects, detect emissions, do some spatiotemporal forecasting, basically do a lot of things to try to get a better sense of sort of what the emissions and land use characteristics actually look like. And there are a lot of stakeholders who are actually working in this area and who use this kind of information. So there are, farmers who use this kind of information to improve their farming practices. For example, depending on how you farm, you can actually improve the amount of carbon dioxide that stays trapped in your soil. And people are using, satellite imagery and remote sensing data to actually detect how much carbon dioxide is being emitted from a certain patch of soil. And there are also, NGOs and government programs like NASA Harvest, GeoGlam, and the Copernicus, the European satellite program, that are actually working on trying to monitor both emissions and land use characteristics from agriculture in order to better get a sense of these kinds of emissions. So this is a really, interesting and useful space here. So there's a question in the chat as to, whether I'm audible. Are others able to hear me? Okay.
Yes, we can hear you. Okay.
Okay, perfect. So I'll keep going. So the last several applications I talked about are all in this category of climate change mitigation. So how do we reduce the greenhouse gas emissions that are coming from either energy-based sectors or from land use? So I'm going to move on to talking about a couple of applications that are on the climate change adaptation side of things. So how do we adapt to the effects of a changing climate, given that we know the climate is going to change to some extent? And one idea here is that in order to adapt to climate change, it would be really great for any individual farmer or city planner to be able to understand what exactly the impacts of the climate change are going to be in their specific location so that they can take local actions to adapt to that accordingly. But the issue today is that global climate simulations are actually really slow and computationally intensive to run. So if you want to run them, you tend to have to run them for a really large spatial aggregation, and you don't necessarily tend to be able to pinpoint, okay, in this specific location, what is the climate actually going to look like? So there's been a real need to try to create more efficient climate simulations that can actually be downscaled in this way. So one way machine learning has been used here is to try to improve or speed up portions of simulations. For example, clouds are actually a really, they have a big effect on the outcome of a climate model, but they're really computationally intensive to model because cloud physics are just really complicated. So machine learning has been used to actually try to approximate the physics of individual clouds in a way that so you can stick sort of an approximate machine learning model into your climate model instead of sticking the complicated cloud physics into the model. And that can actually reduce the runtime of the model overall, and as a result, allow you to maybe run it at a more spatially granular resolution. Machine learning has also been used to try to take certain things that are parameters in climate models, so things that you might be a little bit uncertain about or maybe try out over different values, and actually gather data about them to make our estimates of those parameters more precise. So this includes things like ice is one of the biggest sources of uncertainty in climate models today. And machine learning has been used to gather data about things like ice sheets, like the reflectivity of sea ice, or sea level rise from satellite or aerial imagery so that we can plug that information into our climate models in order to make them a bit more accurate. And here, the kinds of stakeholders that one might want to work with are people like, climate scientists who are actually trying to improve these particular models, and actually local governments who might be, looking to benefit from using these models at a more spatially granular scale, and where it makes sense to understand if the kinds of outputs that are coming from the models are ultimately actually very useful from that perspective. And sort of a last example I want to give falls not in the areas of climate change mitigation or adaptation directly, but in sort of the meta level. How do we as a society make policies that allow us to effectively, incentivize mitigation and adaptation strategies? And the idea with policy is if you're government, you're trying to create the most effective policy possible, one thing you might do is try to understand what have other governments done, what have other entities done, and how can I learn from that information in order to make, policy that is as effective as possible on my side. But one issue is that, there are a lot of policies around the world. There's a lot of text that you have to read in order to understand that. So what machine learning has been used to do is to try to actually analyze these large bodies of text, these larger bodies of policy texts at scale, and sort of synthesize insights from them that can potentially be useful for somebody who wants to then create policy based on those insights. So this has been, machine learning in the area of natural language processing that has been used to, classify or cluster or otherwise analyze text. So for example, this table on the slide actually comes from an analysis of the nationally determined contributions. So these pledges that different countries put in through the UN Climate Change Conference as to how they're going to reduce emissions. This table on the slide comes from a paper that actually tried to analyze these and sort of classify what kinds of pledges or what kinds of actions each government was promising to take. And the kinds of stakeholders who use these kinds of analyses are people like national and local governments. So entities that may want to make better policies and may want to do this in sort of an evidence-based and data-driven manner, but where AI and machine learning can really facilitate that by, again, enabling the analysis of these kinds of things at scale. So what I gave now are just, 7 some odd examples, which I hope give you a sense of the diversity of sectors and ways in which AI and machine learning can be used. And across not just these applications, but sort of the 100+ applications in the Tackling Climate Change with Machine Learning paper, there are a couple of recurring themes that emerge for sort of the role that machine learning can play in facilitating climate action. So one of these is providing information or insight. So for example, I gave the example of, learning from satellite imagery in order to understand the characteristics of, land use or to understand where emissions are coming from. There have also been analyses on satellite imagery to try to detect deforestation or try to learn something about the characteristics of buildings or try to analyze the crop cover that exists in a certain patch of land. There's also been some work, as I mentioned, that has used machine learning to analyze text in order to provide insight on what policies we might want to make. And similarly, there's actually been machine learning used to analyze patents for green technologies in order to understand how to actually then facilitate and fund better development of green technologies. In terms of gathering information from satellite imagery and text gives you information about sort of the present and the past. But of course, there are many situations in which it's useful to have foresight and predict something about the future. So I gave the example of machine learning being used to predict the amount of electricity supply or demand for example, renewable energy that we may have on the power grid in order to help us, more proactively manage the power grid. But machine learning has also been used to do things like forecast the amount of demand we might have for transportation, or also to forecast extreme weather events that may occur due to climate change in order to help, again, like a city or a local government actually adapt to that. In addition to providing information, machine learning has also been used, one big theme, is to sort of improve the efficiency of real world operational systems. So earlier on, I mentioned the examples of, for example, optimizing the heating and cooling systems in buildings in order to, improve the amount of their energy efficiency. I also mentioned this idea of optimizing global supply chains and the way we route freight in order to improve the efficiency of those systems. And there are also uses of machine learning, for example, optimizing heating and cooling, or optimizing refrigeration systems in order to reduce food waste. Similarly, machine learning has been used to try to, predict inefficiencies or breakages in real world equipment before it occurs in order to enable us to actually, fix those ahead of time and as a result, improve the efficiency of those systems. So for example, machine learning has been used to detect leaks in natural gas pipelines as natural gas is transported from where it's extracted to where it's used. And in particular, these leaks in natural gas pipelines are leaks of methane, a very potent greenhouse gas. So sort of detecting those either once they happen or proactively can help you kind of reduce the emissions of methane into the atmosphere. And sort of a last set of recurring themes here is the use of AI and machine learning to help facilitate scientific and engineering workflows that are directly relevant to climate change. So I mentioned how, for example, AI can be used to accelerate scientific experimentation by suggesting, guiding experimental design for next generation batteries or alternative fuels. And AI and machine learning can also be used, as I mentioned, to reduce the time intensiveness of simulations like climate simulations. And this theme also comes up in places like energy and city planning. So at a high level, to recap this, AI and machine learning come up in terms of helping us, gain insight that we can then give to some kind of decision maker, either from, satellite imagery, text information, or also from historical data to create forecasts. Machine learning can help us optimize real world operational systems in order to make them more efficient. And it can also help provide insight to scientific and engineering workflows that are of direct relevance to climate change. So far, I've given a set of examples that talk about, how AI and machine learning can play a role in different climate relevant applications. But I want to talk about some, important considerations to make sure that this work, when you do it, is actually done responsibly and ethically and sort of in full consideration of the context in which your AI and machine learning methods are implemented. So machine learning, as many of you know, the goal here is to really just extract patterns dynamically from large amounts of data. And as sort of, illustrated by some of the examples that I already talked about, machine learning has a lot of strengths. It helps us to scale human insight by taking insights that we might get on be able to apply to a small amount of data and really apply them at scale to a large amount of data. It allows us to optimize complex systems, turn one set of data into insights, and also has been used to integrate with other methods, for example, physical models. But AI and machine learning also have a lot of limitations and weaknesses that are really important to keep in mind as you use these kinds of techniques in climate-related workflows and in other workflows as well. So for example, if you give your machine learning model bad data or limited data, your machine learning model is not going to be able to do magic and get good insights from that limited data. And this is sort of encapsulated from the fact garbage in, garbage out. So you really want to make sure that the data you're putting into your model is of good quality and actually reflects what you want it to reflect. Beyond that, machine learning models tend to inherit biases in not just their data, but also in the assumptions that designers make when putting these models together, and also through their use, in the sense that machine learning models are accelerators of the systems in which they're used. And so if you use them to accelerate a system that, is somehow unjust, then you're not going to necessarily make that better. In fact, you might make that a lot worse. So an example here is if you have a global energy system that incentivizes the use of fossil fuels, and you make energy markets, more efficient, and they optimize the same objective they're optimizing today, you might just make it more efficient to do exactly what we've been doing before. So it's really important to think about what is the system that you're actually accelerating using your machine learning model, and what are sort of the values and goals and objectives of that system. Very important to think about that. Machine learning also tends to assume on its own that patterns are persistent. So for example, if I train a machine learning model with electricity demand data from before COVID-19, and then all of a sudden try to put that model into a world where COVID-19 has happened and the way we consume electricity has actually changed a lot, that model isn't necessarily going to do well. So it's really important to make sure that your model, that the data it's seeing, that the assumptions it's making actually translate to the setting you're actually trying to use it in. And you can do things like, give it more representative data, or put it together in terms of, adding in physical constraints to those models. It can be really important. And the last big thing, this comes up in statistics classes all the time, and is also applicable to machine learning in general. Machine learning is helping you find correlation, not causation. And so it's important to keep that in mind when you're actually implementing these methods. So there's a question from the audience I'm sorry if I'm mispronouncing your name, but Lully. Would you or anyone recommend methods to evaluate the fairness of models? There's definitely a lot of literature on this, and I'm not, a full expert in all of it. But what I'll say is that notions of fairness tend to vary based on the actual domain or context in which you're actually implementing something. And that notions of fairness shouldn't just extend to, is my model, taking data and not making it more biased? It should also extend to this broader notion of what is the system that my machine learning model is being employed in? Is that system equitable? So you both need to get very domain specific, but also make sure that the sort of boundaries of what you're considering fairness and diversity and equity within are sufficiently large to capture all of these different kinds of effects that are important to capture. All right. So there's a question about data sets, and I'm actually going to defer that to the end. Feel free to keep asking questions though in the chat. This is great. Thank you. Okay. And then a couple of last things I want to say is, machine learning is not a silver bullet. I've talked about different places in which machine learning can be applicable, but it's not applicable everywhere. And where it is applicable, it's often only one part of the strategy. Sorry, missing a letter there. So for example, if you want to, optimize buildings and do something really dynamic to manage the heating and cooling systems in these buildings, that's great. But if you do that instead of insulating the buildings, doing this sort of less flashy thing, then you're really leaving a lot of impact on the table. So it's really important to understand how your method fits into this broader context. And again, alongside that, impactful things are often not flashy. And importantly, the work that you do really needs to be driven by end users and the needs of the application that you're actually servicing. So if you're a data scientist and you sort of cook up this scheme that says, okay, theoretically, Priya said that machine learning can be useful for forecasting, so let me pull up some random data from the internet and create a forecasting model, you're probably going to miss a lot of things and nuances that come into play when you actually work with stakeholders. So this is why I tried to put who are the stakeholders on every single slide, to say, really, you should be working with these people and be guided by their actual needs to make sure that the methods you're developing are actually useful and well scoped. And relatedly, as you deploy methods, it's worth noting, sometimes simple methods work. Sometimes there's a lot of temptation to throw the fanciest neural network at a problem, but sometimes something much simpler works very well. I mentioned earlier to think about things like rebound effects, making sure that any efficiency gains that you create, thinking about, do they actually translate to climate impact, or are there other second order considerations I should be thinking about in terms of things like rebound effects? It's also worth noting that AI and machine learning techniques are often developed in society by, entities and people that already have access to a lot of money, computational power, and so forth. And that it's very important in the context of climate action and more broadly to ensure that we democratize the development and access of AI, that we really keep equity in mind as we scope whose problems are we solving, who can actually make use of this based on the way we deploy it, and who can actually access it. So it's really, again, important to keep this in mind when scoping these things out. And throughout this, partnerships are really key, really important to be working with researchers, implementing industries, end users, policymakers, other affected parties to ensure that you're sort of taking all these considerations into account and doing something that is both, useful and responsible. And sort of a last big point I want to make is that, again, while during this presentation, I've talked about ways in which AI and machine learning can be used to help address climate change by helping us, reduce greenhouse gas emissions and adapt to a changing climate. AI and machine learning are general purpose technologies, which means that they can be used not just for good, but also in ways that actually, counteract climate change. For example, machine learning is used in ways that directly increase greenhouse gas emissions, things like accelerating the extraction of oil and gas. They're also used in ways that have uncertain impacts on the climate. So things like AI is used in recommender systems may be increasing the amount that we consume, which then may increase, the amount of emissions that we're emitting due to consumption. It also might do things like machine learning is a key technology in autonomous vehicles, but depending on how we develop autonomous vehicles, they may be good or bad for the climate. If we develop them in a way that entrenches the role of private and fossil fuel transportation, then that might be bad for the climate. Whereas we implement them in ways that actually help us, create more multimodal public transportation and make that, the whole system more seamless, then that might actually reduce greenhouse gas emissions. So there are lots of places in which you might be using machine learning in a way that you don't immediately think of as climate relevant, but that actually might have huge impacts on the climate. And it's really important to keep that in mind. And of course, a machine learning has an energy footprint itself. So as you run a computational algorithm on equipment, the amount of electricity it consumes and where that electricity comes from determines the emissions associated with that. And it also takes emissions to produce the hardware associated with that. And while, data centers only make up about, 2% of global greenhouse gas emissions, remember that I mentioned at the beginning, every single sector needs to go to net zero. So in addition to thinking about how machine learning interacts with other sectors, we also need to, of course, think internally about, what is the impact of the machine learning sector itself. So for those of you who are interested in thinking more about these topics, I would really encourage you to check out the Climate Change AI community. This is a global nonprofit community that aims to bring together people from academia, industry, policy, and so forth in order to help build teams and provide resources in order to do impactful work at this intersection of climate change and AI. So for example, we provide digital resources, including this report on tackling climate change with machine learning that I've been talking through, but also an online wiki, as well as tutorials and summaries of the paper. We also run a series of workshops at the major machine learning conferences, which of course recently have been virtual and sort of open to attend. You can both submit work that you've been working on. You can attend even if you are just, you're not submitting work, but are interested in learning about what others are doing. And we also run mentorship programs so that if you're sort of new to this particular space and want to learn from someone more experienced in order to put together a submission for the workshop, then you can do that. And we also run educational events like a summer school. We also run global funding programs for academic research in this area. We recently closed a, one that was targeted towards OECD countries, and in partnership with another organization, we're currently working on one that is focused on Africa, aims to fund research in Africa that is working on climate change and machine learning. So stay tuned for that. We have an online community where you can meet other people and sort of ask questions, share ideas, and also an online newsletter with job postings, readings, and pointers to events. A monthly webinar series and a virtual happy hour series where you can meet others as well. So in order to learn more and join into these kinds of events, you can just check out the Climate Change AI website. And then last, but certainly not least, this is of course a Women in Data Science, a WIDS event, and the WIDS Datathon for this year is currently ongoing for about the next month. And this year's Datathon is focused on one of the applications that I talked about today, which is the use of machine learning to predict the energy energy usage of buildings based on building characteristics and weather data in order to then target things like energy retrofitting measures. So if you're interested in if you're excited by this kind of area and want to start getting your hands dirty with some data, then I would definitely encourage you to check out this challenge on Kaggle. The link is on the slide. So with that, I thank you so much for listening, for the questions you've given so far, and I would definitely welcome any additional questions.
Thank you. Thank you, Priya, for that fantastic presentation and taking us through all those um, use cases, which we have never even thought about, where we can apply machine learning to so many areas that can impact climate change and help us mitigate, greenhouse emissions as a community. So thank you for that. Any questions for Priya, please post them in the chat and we'll pass it on to her. I'm sure she can speak herself.
Awesome. And there was one I didn't get through during the presentation. And the question was, where do you find reliable data sets regarding climate or emission reports for your models? And the answer really is right now, it depends. So for some of my electricity systems work in the context of the US, I use data from the power system operators in the US who publish things like the amount of electricity demand that they're facing on their system and the prices on the power system. So I'm able to use some amount of publicly available data. But since some energy systems data is, safety critical, or, there are national security concerns around it, it often sometimes involves building like bilateral collaborations with, for example, power system operators in order to build data sharing agreements and things like that. Right now, we are currently on the Climate Change AI wiki, which is just wiki.climatechange.ai, trying to aggregate information about, for different use cases, where are the data sets currently? And we also welcome contributions. If you know of a data set that is, really good for a particular use case and you're able to share that on the wiki, then others can also benefit from that. On the Climate Change AI newsletter, we also publish information about kind of our data set of the month, which we highlight to try to just provide information about what data sets are out there. So these are a few different ways in which you can discover data sets, but it is sort of one of those things where if you want to work with a particular stakeholder in a particular country or a particular context, you often will need to dig for some of these data sets.
So Priya, I think there was one more question about where can I find collaborators and researchers in Egypt? I'd like to find. So do you have like a community? You have an international community, right? So do you have a Slack channel or somewhere where people join in and talk, or is it just through your website?
Yeah, so I'm dropping a few more resources in the channel. And so I'm just typing them, which is why they're not hyperlinking. So I apologize for that.
No problem.
The two resources I'd like to point out. One of them is that we have a community directory at directory.climatechange.ai, where you can sort of discover other people who have signed up for the directory, where they've also often disclosed, the topics that they're interested in, where they're based, and you can find them that way. And then if you put your profile online there as well, then others can discover you. So I definitely encourage those of you who are interested to sign up for the directory. We also have not a Slack group, but actually we use a platform called Circle. And you can find that at community.climatechange.ai. And this is sort of a forum where you can, it's structured a little bit like a cross between Slack and Facebook, but where you can kind of, there are some channels dedicated to different topics. And you can kind of, write in there with questions or comments that you have. There's also an intros channel. So if you say, hey, I'm somebody who's based in Egypt, who else here is based in Egypt, let's chat, then other people can discover you that way. So I would definitely encourage you to check out both the directory and the online community.
Fantastic. Thank you for all those resources. I'm sure our audience will take advantage of that and see. I think there was one more question from Harini.
Yes. And for Ankita, correct, that is the correct link to the online community. Yeah, so I think I see one before Harini from Vivian. So do you have any advice for people who are new to machine learning and want to use it without perpetuating bias? So I would say that, it is very important to sort of both, you want to look at your data and you want to understand, are there any structural factors that exist that could have caused this data to be biased in a certain way? So one very obvious one that exists is there are often more data collection resources in the US than in, say, India. So if you're trying to do machine learning on a data set where you're trying to identify buildings globally, but you're using data from the US, then there's going to be some structural characteristics in that data that don't generalize to other places and could potentially make somewhat harmful mistakes. So understanding some of the context around, not just the data, that was one application, but also the system in which you're employing it, who's going to use it, just thinking through that pipeline and thinking about structural biases, inequities, and things like that, that can be really important. And since it's impossible for any one person to have all of the knowledge associated with both the machine learning method and the context in which it's employed, this is why I say collaborations are really important. If you're working on buildings, you want to be talking to people who focus on, urban planning and urban equity to understand the kinds of considerations that they might be facing. And you also want to talk to affected users. So imagine that you're using downstream a machine learning model to target energy retrofits in a particular community. You absolutely want to talk to people in that community to understand the on-the-ground situation that they're facing. So really seeking out others who have relevant insight on these things and collaborating and brainstorming together about what kinds of inequities and biases may exist for that particular domain is the way to go, because there's no way that any one individual will sort of have all of the considerations in their head like that. Yeah. And I think I see the next question from Harini, which is, how difficult is it to implement these ideas in terms of socioeconomic factors like, capitalism and the growing reluctance and fear towards AI among the public? And I would say that, again, for all of these things, it depends. So climate tech and AI tech, I think in the US are, two of the biggest categories of funded companies right now. So definitely in the startup sector, there's been an identification of some low-hanging fruit where some of these factors are able to be surmounted. So things like optimizing energy use in buildings, you often don't have to wait for like top-down policy. Often you save money by implementing AI relative to not doing that. So there are a couple of places like this where I think there really is low-hanging fruit. You can get a lot of mileage today. In terms of other things, right? In terms of other strategies, there is, of course, you sometimes need to wait for policy or other kinds of factors to go into play. And the ways people have contended with this are, one, actually trying to provide input to that policy itself in order to get that sort of changed or moved forward. Or another is to come up with kind of, creative structures, creative financial instruments combined with creative machine learning instruments to try to provide an alternative route to deployment. So that kind of creativity where you team up with maybe people with a background, with people in data science, with a background in business, with a background in that kind of thing, you can often find sort of alternative routes and creative ways to incentivize something like that.
Okay, thank you, Priya, so much for answering those questions. Great questions from our audience, and yes, a very informative and very thorough presentation on all the different aspects of use cases and in the energy domain. So I'm sure we'll all, I hope we'll make use of some of this knowledge that we're gaining in our Datathon challenge. So with that, Priya, if you can stop sharing your screen, we can move on to our next speaker. Before we get started, I'm going to ask the audience to please turn on their videos just for a promotion for women in data science. If you want, it's optional. I'm just going to take a selfie for them so we can promote our event. Yeah, and it's good to see people from all over the world, so we really appreciate you being here. Fantastic. And with that, we have our next speaker, who is familiar to many on this channel. And she is Erum Afzal. She's the head of Omdena School, who is absolutely passionate about providing quality education in artificial intelligence, data science, and machine learning. She has a master's in information technology from NUST in Islamabad, Pakistan. She currently works there as a media expert guiding postgraduate students in their research. And she's given many talks on data science and machine learning. She mentors many people, and she's a speaker and a trainer as well, and a source of inspiration to many women. So her talk is on deep learning. Welcome, Erum. Take it from there, and I'll make you the host. You can share. Erum, can you hear us? We can't hear you. You're muted. You are muted, Erum. Thanks, Priya. We still
Hello, can
can't
you
hear
hear
you.
me?
Yes, now we can.
Yeah. Thank you so much. I'm so sorry I was unable to unmute myself. I don't know. All right. So without wasting time, I would like to start. Yeah. So thank you, Priya, for such amazing talk and a wonderful insight on domain particularly. So I'm not going particularly about climate and data set relevant to that, but uh, I'm going to talk a little bit about how we can uh, implement machine learning and deep learning techniques in the data set we normally uh, archive or through different channel relevant to climate. So before going into detail, I would like to just brush up basic definition what machine learning is and what deep learning is and how both are differ from each other. So machine learning is application of artificial intelligence that includes algorithms to pass the data and then learning from similar data and then apply whatever is learned to make informed decisions. So we already teach our machines what should be prediction and what should be answers. So that is you can say, in other words, automation of whatever we are feeding to our machines, whereas a deep learning is actually a subfield of machines which automatically pick up whatever could be a good feature to make a useful decision. So if you are familiar with deep learning, you must have heard about neural networks. So neuron is a specific terminology we've been using for to define deep learning, and that match with human brain. So as human brain automatically predict or make decisions, similarly we are trying to make a machine like take decision in a way as humans are taking. So you can see in the picture, while machine learning we have already feature extraction, like we already define these are the features. If these are matching, then we make classification and then we identify some feature like is it nose, it eyes, lips, and so on. Whereas on other hand, if you see this picture, we have human figure and then a deep learning algorithms are trying to extract the feature by itself and then identifying a the classification which of the feature is it. All right. So machine learning, deep learning is a wide field, and we've been deploying it in almost all walk of life. But currently, but today we'll talk particularly about time series data set. So time series data set is a different type of data set. It has its own features, its own you can say depth of the data and how to deal that. As we have image data set, we have audio data set, video data set. So time series data set is actually a sequence of points that occurs in successive order. So it at certain time period we collect certain data. So when we talk about uh, climate change or dealing with the climate issues through machine learning, it means one major data source could be time series, because we are collecting certain activities in environment during different time period. Every single day we come across different situations. So this data, like not always, but most of the data set we can say is time series data set. And since we are talking on the platform of WIDS datathon, so we also have time series data set over here. All right. So in time series data set, whenever we talk about problem statement or whatever issue we are going to solve, so we should know what kind of data we have. So it's normally used to be, we have a set of objects, or we can say features with same structure, for example, real values, vectors, or matrix with same size and fixed set of different classes. Following that, the data collection is the pair of object and classes, which means that each object is associated to or determine a class. Uh, in other words, we can say like the features. So data set, for a data set, a classification problem is building a model that is associated with the object. So in other words, whatever we are talking in previous slides, we say we have certain features and we predict something from based on those features. So whenever you come across any data science or machine learning problem, so there used to be some feature or associated properties based on which we are predicting something. So these are just to polish up our knowledge, like how we do that. All right, so I'm just assuming at basic level, just to brush up what machine learning is and how we build model on that. So when we talk about machine learning, as we have seen earlier, so we have a data set that is a training data set. We apply certain machine learning algorithm on that, and then build a model based on these learning algorithms. And on this algorithm, we input test data set to check how the model is working, what is the working of model, and that is actually called accuracy of model, how accurate our model is. All right, so next we have, sorry. So when we are talking about machine learning algorithms, so we have certain supervised learning model, unsupervised learning model, and reinforcement learning models. Supervised learning models mean our algorithm already know what would be the output. Unsupervised learning model, we don't know actually what the result would be. So for data, as we were discussing in previous slides, we have input points data in term of x and y. X is actual or we can say feature, and y is predictor, like whatever we want to predict in like yes or no, right? And in input we only feed feature, and output used to be y. Right, I don't know what's happening with my slide, so I think I should. So then we have example. Considering a database example, normally we used to share this example most of the cases. Mail is spam or not. So we have a data set, we used to have a data set and certain feature, and based on those learning feature, our mail used to be sent to the spam. But most of us been using email IDs, and we know which mails go to spam. The mail you have not contacted for so long, or suspicious email IDs, and how are how algorithm define what are the suspicious IDs. Probably email starting with you can say number, or the email outside of your organization, or the person who is contacting you for the very first time. So these are few features. Based on that, our algorithm defined like email is spam or not spam, and it's an example of a machine learning algorithm. So the most we might go through these few machine learning algorithm one by one as well, because I just want to show you like applying machine learning algorithm just require only 3-4 lines of code, not more than that. So we have few models like linear regression, KNN, decision tree, random forest, XGBoost classifier. So these are algorithm. These are very powerful. These been used, in data science, but in almost most of you can say applications. And the basic thing we require is just to understand how these models are working and what are the purpose of these models, so that whenever you come across such problem, you should know like this algorithm can perform better in certain areas. Okay, next we are moving forward. Let me give another try. I'm so sorry, I don't know what happened with my system. So when we talk about deep learning, so deep learning is, as I have already shared with you, is always linked with neuron, and neuron mean biological neurons. So how it works is that we input certain inputs, and with input we have attached some weight, right? And weight is some these weights are summed up and uh, is triggered with certain activation function before going to output layer, right? So eh, like for every deep learning algorithm, what kind of the algorithm is, you go through this technique. Like you have input, you have weight is summed up and triggered with the activation function, and then you get one single input from these feature or whatever, right? And we have various activation functions, and this different activation functions are applied uh, differently in different scenarios. For example, we have sigmoid, we have tangent edge function, and we have ReLU function. So if you have our applied machine learning, you must have come across with these function. Like these are activation function uh, be, on behavior of few mathematical equations. So next we have previously we've been discussing single neural network, like how neurons are built and how deep learning is applied. But if we have multi-class you can say data set, and we have to apply multi-layer perceptron, like multi-neurons, not a single neuron. So in that case we have multi uh, uh, perceptron, that is building block used for many learning architecture of time series classification. And how it is used, it's actually is a class of feed forward, like whatever is learned through this layer is being forward to this layer, and output of this layer become input of central layer, and so on. So we define how many layers we want to add in between before going to the final input, and how many final uh, result we have. Like it will not be only yes and no, there could be multiple uh, classes as output as well. So I have just put another example over here just to make it more clear what does mean by multi classes. So for example, we have a few objects with certain classes, and in most simplest way we can say like yes, no, don't know. So we normally, when we say a single layer, so we have only two choices, yes or no. So that is a very simple classification. When we have three participatory object or more than three, then we have to classify more than one object as answer, or we can have multi classes as an answer. So sorry, over here, what we do is that, for example, we have 3 classes over here. So in occurrence of one class, we have to add every single class, although there is no value in between. So what we'll have for object 1, see class 1 is activated, class 2 and class 3 and maybe class n is 0. Similar way, we have object 2. For object 2, class 1 becomes 0 because it lies in class 2. Class 2 is 1, and then restart the zeros. Okay, then we have another the visual, like, and within classes we have this diagram. We have multiple inputs of time series, and we have again multiple layers in between before going to the final distribution of the classes, right? And that's all about convolutional neural network, that is normally called CNN. And in that, like, if we further interpret this architecture into actually how we apply different algorithm and different functions at each layer, so the architecture would be like in this format. So we have input, we have convolutions, as like these are convolutions, and then at internal we have actually different method to reduce the actual neurons. For example, max pooling. Then we have again another hidden layer, normally it's called hidden layer convolution, and then again we have max pooling, right? At the end we have a one flattened layer getting features from this all architecture to the single one, and then at the end we have the one normal neuron that you can say reduce the power, or we can say reduce the feature size. For example, if we have n into m n object and m features, so it means we are increasing exponential power. So we are creating n into m neurons, and that is that will take you months and months to run those new networks and then predict the results. And obviously when we are solving the problems, one used to be like how efficient that problem is along with the accuracy. Like if we are unable to solve a simple problem in a couple of hours or in few days, that would not be helpful, although that is a very efficient algorithm. Okay, so as we can see in the previous figure, CNN are composed of 3 different layers. One is convolutional layer, that is our normal layer. Then we have pooling layer. At pooling layer, we have different method also. And then fully connected layer. Fully connected layer was this one. And usually several convolutional layers and pooling layers are alternate before fully connected layer. Like how many layers we want to add in between, just to as we if you remember, as we do for to make tree, like for forestry, we actually define how many nodes and leaves are required. So in same case, we define how many networks in between are required to make. Obviously at every iteration more features are generated, so network become more powerful, the more layers in between we have. But on the other hand, we may have to compromise the resources, like we need more memory power, more computational power to run, go into these minute details. Okay, then again we have, okay, if you have any question, let me see, we can. All right, sorry, I haven't. What is class? So class is, you can say, a feature as an object. For example, when we are saying a temperature, so temperature is a class, and feature could be high temperature, low temperature, so different values of temperature. So if you see, a temperature is or at abstraction level, on top we have a temperature class, and then we have a minimum temperature maybe going to -12 Celsius, and at highest we can say maybe 45 or 44 or whatever. So and we are collecting data even from one city, so this value will be deviating. So you will see temperature is not a constant value, that is the time series. So it will be changing over different time around the clock. So that we can say it's a class. And someone has already answers. Yeah, it's also a good explanation. It's possible outcome like spam or not spam, those are two classes. What is the difference between pooling and convolutional layer? So pooling is just like, you can say, activation function, where we are actually reducing actual feature size. So sometimes it used to be like picking up the highest what we can say, CROM value. Then in and at abstraction level, we can say it's just like activation function, where we are reducing size of neurons, the size of feature actually. Okay, I don't see any other question. Then we have Anand. So for recurrent neural networks, so if you see for the CNN, we normally used to have we have just let me see, show you. So these are input, then we have certain weight with activation layer, and then we have output. So if you just rotate this image, and now you will see how recurrent neural networks are being applied. So we have input layer, and in between input layer we have certain hidden layers, and then we have output layer. So hidden layers are actually the layer on which we are actual feature engineering or feature selection is being done, just like we did over here, right? So that's the architecture of our RNN. Then we have whenever we apply deep learning, we used to have a learning rate as well with it. So what is the learning rate? It is a hyperparameter that controls how much to change the model in response to estimate error each time the model weight is updated. So it's not a one time model weight is updated, it is updated at every layer. So if we can say that is a one neuron, and when we apply multiple neurons, so the same cycle is being applied with every single connected architecture. So learning rate is like we set it up what at what estimated uh, we can say at what rate estimation error is acceptable, right? So uh, I have added more detail of other basic algorithms over here as well, but I don't want to go into detail, like these are uh, just description how these model are working. I want you to go through a few Kaggle notebooks where you can see how how we can implement these machine learning and deep learning algorithms, and with a few number of line of code we can execute we can apply these models. Or if you have any questions you can ask, otherwise I'll just give walk through a demo how these models are working. All right, so I have not created any one of them uh, because I always believe let's start with whatever we already have. So I have picked up these good and basic code files already shared by someone at WIDS datathon. So I have just picked them up, and I'm just going to walk through how we apply these models. First, we have 5 comparison of 5 simple model, then we'll have another deep learning models as well. So how it works. So for uh, first of all, whenever we apply we start downloading data, or uh, working on machine learning model, we import libraries. And libraries are where you have built-in functions. You don't need to write them by yourself, so you can call numpy to perform operations on that. I'm finding difficult practically use neural net because the limitation on describing variable importance in the model. How would you deal with this issue? All right, so you are saying about on building basic neural network, right? So basically, whenever you are applying any machine learning, not even neural network, but also for a machine learning model. So first of all, we need to understand what we can say problem, what we are going to find from this data. And when we say what we are going to find from this data, it means we have actually understanding of the features and knowledge about the data set we have. So that's why once we'll have what we can say once we'll have proper EDA, we come across uh, you know uh, the actual variables, what are important and how to apply that. I guess then it become easier for you to implement to handle these problems. And I also believe once we'll have what we can say domain expert, he or she can be a non-technical person, but once you'll have that person, you can have a better idea how you are interpreting the actual variable or actual feature in the model. So then we have we are loading the data set. I actually executed them. I don't know if I'm just adding it in case, we have to check anything by coding. So we have imported libraries, pandas for data reading, NumPy also to perform basic operations on data set. Then matplotlib is used to draw a graph or plot a graph. Skylin is a library for algorithms, right? We have machine learning algorithm Skylin for pre-processing, then linear model, linear regression, K near neighbors, decision tree, random forest, XGBoost. Then we have these are for K-fold, and these are for more model validation libraries, right? So I normally don't prefer to call every library before sort of the code, because uh, that will confuse you. So at moment we only need pandas just to import our data set, our load data set, because we are reading our CSV file using function, a CSV read function from pandas. So when we write over here pd.read underscore CSV, it means we are using read underscore CSV function from pandas. Hard is used to check by default 5 values in the data set. So at moment we have 5 rows and 64 columns in the data set, and there are different type of values over here. You must have gone through that. Then we are starting. So to load data, we need only one line of code, right? So if I start my code from here, just to write import pandas as PD, and then simple this line of code. So it means I have already loaded my data. So to load data set, you only need 2 line of code. Then we will start exploratory data analysis. So exploratory data analysis means you are exploring your data set. So over here, we are not applying machine learning or deep learning or transfer learning or any kind of, technique over here. We are just exploring data. We are just looking like what is the spread of data. Is it a normally distributed data set or not? Is there a biasness in data, or there are we can say missing values attached with it or not? And how visually it looks, are the values balanced or not? If the values are not balanced, then the class have more values will be predicted more in our algorithm, and that can predict biased results. So that's why we explore our data set, and that also solves the problem. As you just asked, you don't know how to actually know about the variables why building your neural networks without using uh, building your own neural network. So train the underscore df is just a name of data frame, and info mean we are just checking which actually information of the values are columns in in our CSV file. So you can see over here air of vector have 7575 value, you can say count value entries. There is no null value, and data type is int64. Then state vector is object. Then we have floor area, that is float, and we don't have null value over here. No, non-null is not is not actually counting over here. So we can see null values are in last 4-5 columns. Rest of the column have full value. So we have uh, uh, days with fog have less values, 29,000. So from 75 to 29, so it's more than 50% missing values. Then wind speed have missing value, then direction peak have missing value. So you can check from this, like simple, you can say this command, how many missing values are there. Then you can see that's the just description. If you want to see what are the name of columns, you can simply write dot columns, whatever your data frame name is, then you can write dot columns. Drop building ID. So when we run algorithm or execute anything on the data set, so it computation power includes. So we normally keep only relevant columns in our data set and remove rest of them. So at moment we don't know which of the uh, uh, features are important or which are not, but we definitely know id doesn't play any role in computation. So we can always remove id just to make processing, we can say, computation power efficient. Otherwise removing it or don't remove it doesn't make proper, you can say, have a significant important in creating or applying machine learning algorithm. Over here we are seeing how many rows and columns in both train and test data sets. So for that I need to execute train CSV as well. So, sorry, test CSV as well. So I'll execute this one, and then ID is not found. Why it's saying ID is not found? Because when I have executed it before, it have deleted ID already. So that's why it's showing an error. So we have both are training data set. It should be test data set, sorry. So we have test data set, we have train data set, then we have if we want to drop duplicate values, we can create it as 0. We are saving as it is, and then train dot drop duplicate. It's the function in data frame as well that drop duplicate values. And similarly we are actually looking when we want to see how many rows were there as a duplicate. So we are checking actual data set with dropped value. Then again we have missing values. I'm not going into detail over here. I just want to show you algorithm, and then if we'll have time I'll get back over here. So we can go to feature engineering, and there is no a standard set of rules like you can go to these point and these can help you to visualize. So these are just, you can say, heuristic how you move forward while exploring data sets. So it's up to you, or you can play around the data set and see how many missing values are there, how to encode them, which how if the more than 60% values are missing, you can drop that or if you want to fill the missing value. So there are again methods you can impute, for example 0 value over there. If that does not affect your final result, sometimes 0 is a meaningful value, so you don't impute that value. Sometimes you fill up with average value, sometimes you fill with certain algorithm, for example creating group and filling in nearest, taking mean of nearest group of 5 or 10 values, something like that. So again that is actually the heuristic you play around and see how you can make a good data set to input the model so that you can have accurate results, not in term of accuracy, in term of true meaning. uh, like model accuracy 98% doesn't mean like it will work very well when you know uh, perform or test the data set. Then categorical value, so you also know algorithms are applied on numeric values. So if you have objects, so you need to change those object values to numerical equivalent of numerical values. So what we normally do, we decode them. For example, male female are converted into 0 and 1, and if there is a country code, you change that. So if the values are categoric in categories, you need to change them, code them to make a numeric value out of that. Scaling feature, then model building. Yeah, so for model building, so we, as I have told you, we just need to write a few lines of code, like just 4 lines of code are sufficient to create to run an algorithm. And let me show you how. So for example, importing library, model library, of course. Then we have function call, and that will be ML algorithm. And then we have a fit model, like fitting your this function on the data set, train data set, and then you can test your model. You can test accuracy, prediction, or whatever you want. So only if you write these 4 steps, so you are done with, like, you have applied machine learning model on your data set. So for example, I have imported linear regression, right? And then I have actually embed what we can say, append that that model on my data set, where I have this one. So that's the actual. So we have, let me bring this code here. It's random forest. All right. So I have called library random forest, then call the function random forest, and then fit it on train data set, and then I have made the prediction. So only these 4 lines of the code are required to apply any kind of machine learning algorithm. And obviously, if you have understanding how that model work and what are the requirement of these models, then you can apply that. Okay. Yes, EDA is done on both train and test data set, of course. Join now only. Could you? Okay, Preeti, I guess Nishin can share the schedule with you.
Yeah, I can share it later.
Yeah,
Let's talk.
all right.
Let's let her get through her presentation.
Okay. So that is about a machine learning model. So if you have any question on machine learning, I would love to reply you over here, and if not, then I'll move forward with applying one of deep learning model like LGVM and other. Okay. So here is another uh, a good I found a good Kaggle you can say code book. Again, we have imported libraries, few libraries, NumPy, PD, pandas as PD for data frames, matplotlib for plotting the graph, cbon is also for plotting the graph, and that is actually from when we have format string, that is also how did you select. I'm coming to this one, cross validation as well. Okay, let me see if I can run this one as well. Again, we have imported the libraries and drop ID columns, storing features, categorical and numeric features. Describe, I don't need this one. Dealing with null values. So you see over here, we define a function null value, storing null values in array, and then on each we applied a loop on each column. If there is null value, sum that up, and then making a percentage of that, and then returning that to this one. Let's execute this one also. Then we have categorical features over here and plotting them as well. So years, so you can see from year count, you can see how many values are there from 1 till 6. Then we have year factor. We have, the equal block. We don't have different values. State of vector, you can see these values are more or less equal. These values are, we have more values in state 6. So we might have to normalize data set over here. Again, test data factor. So if you can compare both data set visually, like which values are over here, residential values are less than a commercial value, but in trained data set we have less commercial count than residential count for building class, right? So according to facility type, like the certain values in our categories like grocery stores, count of that, public assembly, social meeting. So while visualizing the feature, we come across you might not well aware what is the spread of data, like how many values are there and which state have how many count in each state, and the categories in feature type, which category is the highest one. So we might have to look upon these categories. So for just storytelling through data, we can do that only with visualization. So visualization gives us a better impact to just compare both train and test data set, and we can normalize the data set before feeding them into any of the model. So you see over here, service dry cleaner or laundry values are very high, and over here multifamily uncategories values are very high. Then we have similar, these are actually graph from categorical features. So we have only 3-4 categorical values. So if you see, if you remember in our previous notebook, we have checked like the data type of values. So the object were representing categorical values. Now we have numerical values. So for numerical values, we used to have different kind of graphs. For categorical values, we normally use bar graph. For numeric values, we can draw like different line graphs, different graphs, just to check the continuity of those values. These are also a good visualization just to analyze. So you see over here how the factors are moving. Right, and we have actually the different train and test data set values, and that can give you a better visualization. What is the spread of your data, and what should we expect? you know uh, uh, at moment we have more value in these graphs are more or less similar one. For example, over here, so you see there is a huge difference between both values, although the value count is more or less similar, but the value spread is different one. So the result can obviously affect from only this spread of data. Then again we have facility type in train and test data set. And then another feature is finding correlation. So you see we have already seen, I see. I'll definitely share the code with all of you. I'll share that with Nishin so that you can have copy of the code. Basically, I took that from the Kaggle directly. Okay, I am not spending much time on these. So basically we can find the correlation also. So correlation also give us a better idea, like it can also help us out which variables are correlating, like negative correlation and positive correlation. So if we draw a correlation graph, that can also help us out in choosing the best feature while doing supervised learning, because we know these two, like on the actual data set, these two values have a strong correlation. So it means these are important features. And in other way, if we want a negative correlation and there is a strong negative correlation, we can keep those values. So on average, grocery store, food, milk, data centers, and laboratory have a higher site target value. So they have actually checked it through this one. So I think I have missed some I have missed any cell before. Okay, now I'm just going to add, let's say LGBM. I'm going to apply only LGBM model over here. So how we'll do that? We will call the function, and then we'll apply that on algorithm. So that's the base model, right? So that's what I've been telling you, how many iterations are required. What is objective function over here? We have gone through 3.1. What is the learning rate? What is the maximum depth of the neurons? And how many number of leaves would be there? And are we going to run this on CPU or GPU? So over here, we just forget about these one at moment. These are actually, model validation. So let's not take these into consideration. So we have called LGBM over here while calling those libraries. So we call that over here, and then we have just set the parameters regardless anything. So that's what I also always recommend. Just try to apply the simple model first, and then we are fitting it over here on train extra test train and test values, and then we see what are actually result of this simplest model before going on any data validation, and you can say uh, uh, any data treatment on the model. Once you'll have that, then you can go back and apply model evaluation technique on that, model validation on that, and see like model validation actually gives you like whatever prediction is, how much is it true, what is how we can balance the class. So it validates your model before going into test.
Hi, Erum. Would we be able to wrap up in a few minutes, or I can ask you
Yeah, it's
a
almost
little
done.
longer?
No, it's
Yeah, I know there's a
done.
lot of material, and you're showing so many rich things that all of us would be very eager to learn and all. But in the interest of time, yeah, you can stay a few minutes over. That'd be great if the audience can do that, so she can wrap up in a nice way.
So I have already that is just to walk through when I say we can write a model only in 4 lines, so it means we don't need to go into, like, my purpose of going through this one was that if we just write 4 line of code and test whether it is working fine or not, because most of the time it used to be very frightening, like how to run this long code, and what are what is what these line meant for. So the purpose to show over here is go through the basics, like what are the requirements, and stick with that initially. So once you know the working of model, and then on upper layer you can always improve your model by using validation techniques. And definitely I'll share the link with Nishreen. These are amazing uh, code links you can go through by yourself and check apply with them in your free time.
Awesome. Thank you, Erum, so much. That was a good overview of deep learning, as well as taking you through some very essential elements of developing a machine learning model, right? Start with the simplest, look at your data, analyze it, think about what kind of variables you have, how to deal with them, if there's imbalance, how to deal with them, and so on. So these are very critical and essential parts of a machine learning solution, and you're aiming for good data quality, so that the results that you get out, when you get to your results are more reliable, they are more accurate, and you can trust them, right? So it takes people should spend more time, and she will agree with me, is on looking at your data and massaging it so that it's proper, you understand it, make sure it's balanced, and it doesn't have as previously even Priya mentioned, that we can sometimes include biases and things like that into our models also. So being keeping that awareness, some limitations in mind, is absolutely essential for a robust machine learning solution. So thank you, Erum, so much. I know it's pretty late for you. She's joined us all the way from Pakistan, so I really appreciate it. It's really late out there, and she's also a fellow ambassador. And so thank you so much for being here tonight. And thank you for the audience as well. The recording will be shared. Whatever links and things like that I get from the speakers, of course, I will share with you. I hope you had a good learning experience. And remember, we have 3 more weeks to go, where we have many other presenters going through different topics and aspects of data science and machine learning. So I hope to see you all there. The schedule is actually on our Eventbrite page. So if you can go to that, and I think somebody has posted the link in the chat. So please look at that. It's the schedule. Every week we have 2 to 3 speakers. Every weekends, and we're starting Saturdays at 9 a.m. Pacific or 17 UTC. So I hope to see you all at the next sessions. I hope you learned something today from our fantastic speakers that are here. And yeah, have a good rest of your weekend. And yeah, hope to see you next. And feel free to connect with all of us. This is also about making connections, right? This is your community. This is your data science community, where we try to encourage and learn and support each other. So feel free to connect with us on LinkedIn. You can see our names here, so feel free to do that. All right. Have a good rest of your week, and thank you all.